तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So let us see now how we could write down the evolution equation for the state vector, the Schrodinger equation, for a simple model system, namely that of a particle moving in one dimension, and that will give us a hint as to what this Schrodinger equation should look like in more complicated cases. So let me look at one dimensional motion, or even simpler than that, just a free particle moving on a line. This is the simplest of motions, no potential of any kind whatsoever. So let us start by writing down the following. The Hamiltonian of the system, so you have a particle moving on a line, the x axis, free particle, and we should like to write the Hamiltonian of the system down. The way you go about it is to write the classical Hamiltonian down, which is p squared over 2m. It is a single component, so there is no vector here, it is just on the x axis, and that is the Hamiltonian. There is no potential energy at all. The quantum version of this is the classical Hamiltonian. The quantum version of this is to say that the Hamiltonian operator, and let me use a caret up, a superscript there, a caret, to denote operators. Whenever I would like to distinguish operators from functions or numbers, C numbers. Later on we will drop it once we get a little used to this. This thing here is P operator squared. This is the momentum operator. Now remember that with every physical observable, by postulate we associate a self-adjoint operator with real eigenvalues. So this operator is a function of that operator here, a very simple function in this case, just p squared over 2m, that is it. And now we would like to write down the Schrodinger equation. The Schrodinger equation for this particle would be IH cross d over dt psi of t, let us put capital psi of t for the state vector, is equal to the Hamiltonian operator acting on psi of t, this fashion. Okay. And we have to solve this equation, and of course this is equal to p operator squared over 2m on psi of t. Okay. And one would like a solution to this equation given the initial state. Of course we know the formal solution already. The formal solution states that psi of t at any instant of time is equal to e to the minus I over h cross h operator t acting on psi of 0. So you have to take the momentum squared operator multiplied by these constants, exponentiate it, and then act on the initial state in order to find the state at a later instant of time. This is quite a formidable task. But what is it we finally want to look at? What are the attributes of this particle? Well, it is a particle moving in one dimension, then classically of course it has a coordinate x and it has a momentum p, and these are the canonically conjugate variables such that this is equal to 1. That is the classical Poisson bracket relation. Quantum mechanically this would become x operator, p operator is IH cross times the unit operator, because according to a rule for quantization, Poisson brackets go to commutators divided by IH cross. So we would like to find out how to exponentiate this operator here and how to act on that thing. Now whenever you have operators, vectors and so on, you always choose a coordinate system. Only then can you write down the actual components of a vector. In exactly the same way, whenever you have an abstract problem of this kind in quantum mechanics, you must choose a basis, you must choose a basis set in terms of which you express everything else. As you realize, once you give me Cartesian coordinates, a Cartesian frame, I could write down the numerical values of the components of a vector, otherwise the vector remains an abstract vector. In exactly the same way, I would like to choose a basis. Now what kind of basis would be convenient for this problem, for this, that's exactly the question one has to answer right in the beginning given the system. What kind of basis would be convenient? Well, obviously a basis in which, a basis consisting of eigenstates of some physical quantity associated with the particle. Now what are the physical quantities associated with this particle? Its position and its momentum, that is it, it has no other physical attributes whatsoever, everything else is derived function of these two things. Therefore one would like to use a basis, and let me call it the position basis of ket vectors which are eigenstates of the position. But what are the possible values of the position? Every number from minus infinity to infinity. Therefore I introduce a set of vectors, and let me denote it by just x here to show that it is a position here, such that minus infinity, well, let me introduce a set of basis vectors such that x operator acting on a particular x, say x naught, some given x naught, some given number here, is equal to x naught on x naught. This is an eigen basis, in the sense this operator, the position operator, acting on this ket vector labeled by x naught gives you just x naught acting on x naught. This is an eigenvalue equation. The operator, eigenstate, eigenvalue, eigenstate. I should really put psi here and put a subscript x naught to show you that this is the state vector corresponding to position x naught, but that just clutter of notation, you do not need to do that, I could just write it in this fashion. So whatever is inside here is already the label for the corresponding eigenvalue here. So this is a crucial sort of thing we must appreciate. This is an operator, this is an eigenstate, and that is the eigenvalue. Okay. And what are the possible values that x naught can take? Every number from minus infinity to infinity. So minus infinity, less than x naught, less than plus infinity. Okay. I formally introduce such a basis. Now this basis is different from the ones you have been used to a little earlier. In what sense? It is a continuous basis, because it is not labeled by 1, 2, 3, 4, 5, 1, 5, 2, 5, 3, etc., but it is a continuous basis. Therefore if I orthonormalize it, and there are technical problems here with a continuous basis, but we will not worry about them for a moment. If I pretend that I can do this, define rigorously a continuous basis, then the orthonormality relation, what would that look like? That would look like x, any other x equal to what? This should be 0 unless x equal to x prime, but it is continuous. So instead of the Kronecker delta, you have the Dirac delta. So this is delta of x minus x prime, where x and x prime here refer to the eigenvalues corresponding to this ket and this ket here and this bra. They are numbers. These fellows inside the ket or bra, they are actually labels. This is orthonormality. What is completeness? What would that look like? What would that look like? Because go back and look at something like phi n, phi m equal to delta nm, and summation over n phi n, phi n equal to the unit operator. That was orthonormality, and this is completeness. Now what would that look like here? You need an integral instead of a summation. So you need integral dx x with x equal to the eigenvalue, unit operator. This is completeness. Okay. Now we come to the probability interpretation, because if you give me an arbitrary state of the system psi of t, I can expand this psi of t in this orthonormal basis. Therefore, I can write this as equal to a summation over n. If I have an orthonormal basis labeled by a number n, it is of the form Cn phi n. That is the way you normally would expand this. But now I must replace this by an expansion in a continuous basis. Therefore, I have an integral here over dx, and I have an x here, and what was this Cn earlier? This guy Cn was equal to phi n psi, that is what it was, right. So what should I put here? A bra vector x psi of t. Please notice I could have moved it to the right hand side and used the fact that dx ket x bra x is just a unit operator. So I have just rewritten that in a trivial manner here. You see what I am saying is, you could have written psi of t equal to 1 times psi of t equal to integral dx x x psi of t, but that is equal to integral dx x psi of t with x, because this is just a complex number, and therefore you can move it back and forth. This is how the expansion goes. These are the coefficients, but the coefficients now are not labeled by a discrete number n, but by a continuous index x. Therefore, what should I call this? This is equal to integral dx, well I should call this some number, right, some quantity, x psi of t. What should I call this? What notation should I use for it? Well, it is a coefficient, so I could say it is c, instead of n I have an x and then a t. But I want to remind myself that it is the coefficient in the expansion of this ket vector with a psi. So let me call it psi x of t, but x is continuous, so it is stupid to put it down as a subscript, right. So let me put it inside and just call it psi of x comma t. That is a reasonable thing to do. The t dependence comes from the d dependence of the state vector, the x dependent comes from this scalar product here of the state. Now what is this quantity? This is the probability amplitude that when the system is in the state psi of t, it is in a position eigenstate with label x. In other words, it is the probability amplitude that the position is x at time t, and the mod squared of this, is the probability amplitude, or rather probability amplitude density, because this thing is now a continuous variable, that the position lies between x and x plus dx. If I multiply it by dx, I get the probability that the position lies between x and x plus dx. And what do you call that psi of x comma t? What do you call this? So now we begin to see what is this quantity. That was equal to, by definition, that was equal to psi of x comma t. What do you call this quantity in quantum mechanics? The wave function. This is the wave function. This is how the wave function arises. and we will write down differential equations for it and so on, but it is just the coefficient in the expansion of an abstract state vector in the position basis. Since it is in the position basis, what sort of wave function should I call it? Position wave function, position space wave function, this thing here. Or the wave function in position space, or the wave function in the position basis, but that is the wave function you are most used to always. So this is how that psi of xt which you saw for the first time in chemistry 1, this is what it is. It is the coefficient in the expansion of the state vector of a system in the position basis. Of course if you are working in 3 dimensions, the particle is moving in 3 dimensions, then it is not labeled by just one number here but by x, y, z or r, theta, phi, does not matter. You could express this coefficient either in polar coordinates, spherical polar coordinates or whatever, Cartesians, whatever you like, and it might have more than one label here. So please appreciate the fact that the t dependence here comes from the dependence on t of the state vector, that is dynamics. The x dependence comes because you happen to have chosen the position basis in which to expand your state vector. Now you could say, oh, I also have a momentum, after all this particle has a momentum, why can't I choose the momentum basis, why can't I choose eigenstates of the momentum? Certainly you can, that is called the momentum basis or the momentum space function. So this would correspond to a set of ket vectors P labeled by P such that P operator acting on some particular momentum eigenstate P naught would give you P naught times this guy, and of course this immediately becomes P with P prime is delta of P minus P prime dp, and then a P with P is the unit operator. I could do exactly the same thing, I expand the whole thing in the P basis, and then what do I get? I get psi integral dp P with psi of t P ket vector, and I would like to call this guy something or the other, P psi of t equal to what? What should I call it? Everything is in the notation, you have to choose your notation properly. It is a coefficient, but it is a function of this continuous variable P. So let me call it psi and put P comma t. Do you agree? Do you agree with this notation? But you see I have already used that function psi for the position space wave function, so I need something else. What should I use? Well, I could use psi prime, but that looks like the derivative. I could use phi, but then that tells me that is another ket vector phi. I should have psi there, but I shouldn't use a prime. What should I do? If I use bar, it looks like the complex conjugate. If I use star, it looks like the complex conjugate again. If I use, what should I do? If I use cap, it looks like an operator. No, I am serious. I mean this is when you are reading a book, there is a meaning to everything, there is a reason why you do things. Tilde is a good idea, good. Psi tilde does not conflict with anything else. Half the battle is won once you frame the notation properly and you know exactly what you are talking about. So what should I call psi tilde of Pt? What would it be called? Momentum space wave function. This is the momentum space wave function for the same state. Do you think this and that are related? By the way, what is the interpretation of this? what would the mod squared of this look be? It is the probability density that the momentum has a value p, specific value p. You could ask, in that momentum eigenstate what is the value of the position? We come to that slowly. They can't be simultaneously made sharp, made precise. So the point is, a momentum eigenstate cannot be a position eigenstate, and a position eigenstate cannot be a momentum eigenstate, which brings us to the next question. If I give you two operators corresponding to a physical system, can I find a simultaneous eigenstate for them or not? We are going to answer that very, very important question shortly. But first, what is the relation between this guy and that guy? It is just a change of basis, so we can knock this off right away. Psi tilde of p comma t equal to p with psi of t, and I want to relate it to psi of x comma t. So what should I do? When in doubt, insert a complete set of states. When in doubt, put in always a unit operator. So the unit operator can be written as dx x x, that is the unit operator, and that acts on psi of t. This guy is the ket vector on the right hand side, it acts on that. So what I did was to insert a unit operator. But what is this guy? That is psi of xt. So we have this crucial relation which says psi tilde of p comma t equal to integral over dx p x psi of x comma t. So the momentum space wave function is related to the position space wave function by this relationship here. And what does the physical meaning of this quantity? This is the probability amplitude that when the position of the particle is x, its momentum is p. This is a probability amplitude. And of course we know at the back of our minds, we are going to prove this, we are going to find that number, we are going to actually compute this number. This thing here, you know from the uncertainty principle that if you specify x sharply, precisely, the uncertainty in p becomes infinite, because delta x goes to 0, delta p must be infinite so that the product can be remain greater than h cross over 2, which means all possible p's must contribute, which means that this is a number whose modulus squared is independent of p, should really be uniform. So a constant would be a good guess, but then nothing happens, this means nothing moves, there is absolutely no change at all. This number here we will compute it backwards from the commutation relation. We could also put it in as an input, but we will do this from the commutation relation just to show you that it is completely rigorous. This quantity here will turn out to be e to the power I p x over h cross, where p and x, mind you, are numbers, they are numbers here because they are labels here. These are kets corresponding to certain labels, values. And then what does it look like? If this is the situation, and I have anticipated myself, if this is the result, that it is an integral over x e to the ipx psi of x comma t, what do you call such a thing? The Fourier transform. It is just the Fourier transform. So it was a happy choice that we actually use the tilde here. It is indeed the Fourier transform with respect to x. So I had a hidden motive in agreeing to this tilde here. It is just the Fourier transform. What would then psi of xt as a function of psi pt in terms of psi tilde, how would it look like? What would it look like? It would look like exactly the same thing. Psi of x comma t would be all p's x with p pt. This guy here is the complex conjugate of this guy, and I have already mentioned, jumping a few steps, that this is equal to that. So what happens if you took the complex conjugate? You get a minus sign, therefore it is the inverse Fourier transform. So this neatly meshes, and now you can see how for canonically conjugate variables like x and p, a coordinate and its generalized momentum, Fourier transforms automatically enter the picture, very naturally they enter the picture here, and the description of this abstract state either in the position basis or in the momentum basis are completely equivalent. You might want to do one or you might want to do the other depending on whichever is easier in a given problem. In most cases it is easier to work in the position basis for a reason which will become clear very shortly, but it is not necessarily always true. There are important problems where it does not matter which basis you work in. Can you guess a priori which basis would it be easier to work in if I look at the motion of a particle in a potential? So the Hamiltonian now is p squared over 2m plus a potential energy which is also an operator, it is a function of the position operator. Okay. Why do I say it is easier to work in general in the position basis? We will prove this, we will see, you will see explicitly, but what would be your guess? You see, when you have a system like this, when you have a Hamiltonian like this, if I take a particular x0, a position ket vector, and I apply h to it, so h acting on it is p squared acting on x0 over 2m plus v of x acting on x0. What is this equal to? We do not know, a priori we do not know, because we do not know the action of p on that. We know the action of x on that, but we do not know the action of p on that as yet. So we leave it aside, it is some p squared over 2m acting on x0 plus what is the action of this on that? Well, x operator acting on x0 produces x0 times x0, so x operator squared produces x0 squared and so on. Any function of x operator produces the same C number function. So I hope you appreciate the fact that this is exactly equal to v of x0 on x0. This is an operator, this is just a function, because this is an eigenstate of the position operator, therefore any function of the position operator also for that too, it is still an eigenstate. Is this clear? This step, it is crucial. It's crucial. Is this okay? Now look at what happens if you did this to a momentum eigenstate. If you did the same thing with a momentum eigenstate, I apply h to a p naught, what would this give? You would have a p naught here and p operator acting on it, so what would the result be? Just p naught squared on p naught plus what would this be? We do not know, it is v of x acting on p naught, and unless you tell me what is the effect of x operator on a momentum eigenstate, I cannot proceed further. But you immediately see that this v of x could be quite complicated, e to the x, it could be anything, all sorts of powers of x, inverse powers of x, it could do complicated things. On the other hand, the kinetic energy is always p squared over 2m in non-relativistic in this situation. Therefore if I find what p operator does on x0, all I have to do is to find what p squared does. That is a fairly simple task, but this guy could be a horrible function, may involve exponentials, logs, transcendental functions, and that would have to act as an operator on p naught, and in general it is complicated, very complicated. This is why, since the kinetic energy is always just the square of the momentum, but the potential energy is not a simple function of x in general, you have problems. What situation can you think of where it does not matter which basis you use, they will be completely symmetrical? The harmonic oscillator, because that is the case in which you get x operator squared here and it is completely symmetrical. Now you see the special role played by the harmonic oscillator. that is the one in which the position and momentum bases are completely equally difficult or equally simple. So it is a very special Hamiltonian, because this quadratic form in x and p is completely symmetric under the interchange of x with p. That does not happen in other problems. This is why in normal potential problems you always use the position basis, but it is not necessary. You could use the momentum basis, you could use other bases, but for a particle moving in one line on a line, it is just the position and momentum, there is nothing else. For 3-dimensional motion, of course, there are other things like angular momentum and so on, and we then have to ask what are the operators which commute with each other. So now let me make a few statements about mutually commuting operators. After that we have to come back and address this question of what does the momentum operator, what is P on x naught, we need to find out what it does. Actually we do not need to answer this question, it is a sort of meaningless question in some sense, it is not relevant, because clearly P operator or any operator acting on a ket vector is going to take you to some other ket vector. In this case what we are interested in always is working in the position basis, always. When you say I am going to work in a basis, it means you are always going to put a scalar product on the left hand side with another basis vector belonging to the basis. So it is clear that I am not so interested in this question as in the question of what is x P operator x naught, because I am always going to work in the position basis, so I am going to do a scalar product with this guy here, and I need to know what is this guy. We will compute that number, compute this. Any answers? Can you guess what is going to happen? It will turn out that this will involve the derivative, partial derivative with respect to x. It will turn out to be minus IH cross d over dx of x with x naught. More generally, if you have an arbitrary state psi here, this, and let me write the answer down, we come back and look at it, this thing here will turn out to be minus IH cross delta over delta x, x with psi. But this is what you call the wave function in the position basis. So this is the reason why one identifies the momentum operator with minus IH cross the gradient operator, because that is the representation for it in the position basis. When acting on position space wave functions, the momentum operator acts as if it is just minus IH cross the gradient operator. It is a representation of this operator, so one must not mistake the person for his clothes. There are these abstract objects, there are these abstract states, and the wave functions, these representations and so on, these ways of writing the operator and so on are representations of these objects. But first, before we get to this, let us write down a few key results. Simultaneous eigenstates. Suppose you have two operators, I will drop this the cap on top of these symbols for simplicity here. Suppose you have an operator A and an operator B belonging to a certain physical system, they are both self-adjoint Hermitian operators, so A equal to A dagger, B equal to B dagger. The first result we need to ask is, can I find simultaneous eigenstates of A and B? Can I find eigenfunctions and eigenstates which are common to both these operators? In general the answer is you may not be able to do this. In general, if you just give me two arbitrary operators, there is no reason why the eigenstates of one should be the eigenstates of the other at all. But you might expect that some eigenstates of one are some eigenstates of the other, there may be some overlap between them, may or may not be. Okay. Now we want to make this precise. The first question is, given the fact that these operators are Hermitian, self-adjoint, does it mean I can always find their eigenvalues and eigenstates? And the answer is yes. Let us do this from matrix theory. Given a matrix A, an n by n matrix, under what conditions can you diagonalize this matrix? because I would like to diagonalize it, find the eigenvalues, find the eigenvectors. Finding the eigenvalues, by the way, is a trivial algebraic exercise in principle, but finding the eigenvalues and the eigenvectors, diagonalization means finding the eigenstates of this matrix, is not always a trivial exercise. Under what conditions can you diagonalize a matrix? You can always diagonalize a matrix by a similarity transformation if A dagger equal to 0. In other words, if a matrix commutes with its Hermitian conjugate, it is called a normal matrix, and such a matrix can always be diagonalized by a similarity transformation. This is a sufficiency condition. It is not actually necessary, it is a sufficiency condition. And these are all Hermitian matrices that we are talking about. So of course A dagger is the same as A, and therefore A commutes with itself as a normal matrix. So all our operators, physical operators, can actually be diagonalized. We can always find their eigenvalues and eigenstates in principle. So that question is not going to bother us. Under what conditions can A and B be simultaneously diagonalized? That is the question they are asking, and the answer is if A and B commute with each other, then you can simultaneously diagonalize them. In fact, you can go further. If A and B commute, so let me write down the set of statements. If AB equal to 0, the same similarity transformation can be used to diagonalize both. Pardon me? It means I can take this matrix A, they are both of the same order, say n by n matrices. I can take this matrix A, take this matrix B, and use the same similarity transformation S such that SA S inverse is diagonal, SB S inverse is also diagonal. Yeah, I mean simultaneous not in the sense of time or anything like that, but with the same similarity transformation. That is the first statement. If A and B do not commute, then the question is what can I say, and it is a common misconception to assume is not identically 0. It is a common misconception to assume that if you have two operators A and B in a quantum mechanical system which do not commute with each other, then you cannot find simultaneous eigenstates. That is not true. That is not true. The statement is you cannot find a complete set of common eigenstates. You may find one given eigenstate which is common to both of them. For example, 0 may be an eigenstate of both operators, but not a full set of eigenstates. Incidentally, if they commute with each other, does it imply that every eigenstate of A is an eigenstate of B? This does not mean that, does not mean that at all. Let me give you a very trivial simple example. Take functions on a line f of x, all possible functions on a line, then we know that the following is true. We know that the identity operator acting on f of x is f of x itself. In this function space, the identity operator acting on f of x is f of x. So the identity operator, every function is an eigenstate of the identity operator with eigenvalue 1. Now consider the parity operator. Consider the operator p such that p f of x equal to f of minus x. It changes x to minus x. That is the parity operator. What happens if you apply this parity operator twice? P squared f of x equal to, this is p acting on f of minus x, and therefore it brings you back to f of x. So this means, since it is true for every function, it means that the square of the parity operator is the identity operator. Therefore the parity operator commutes with the identity operator. P commutes with p squared. But is every eigenfunction, every function also a parity eigenfunction? What are the parity eigenfunctions? Even functions or odd functions, right? Because an eigenfunction of the parity operator, if I call it phi of x, then it says p phi of x equal to phi of minus x, and but this must also be equal to lambda phi of x. If this is an eigenfunction of the parity operator, it must be equal to lambda phi of x. So it says phi of x must be such that phi of minus x is lambda times phi of x. Moreover, if you apply twice, it implies p squared phi of x equal to lambda squared phi of x, and p squared is the identity operator, so this is equal to phi of x itself. This immediately implies that lambda equal to plus or minus 1. What do you call the case lambda equal to plus 1? Even functions, and the case minus 1 you call odd functions. So even functions are eigenfunctions of the parity operator, odd functions are functions of the parity operator. But every function is an eigenstate of p squared. So p squared has a much bigger set of eigenstates than p itself. P and p squared commute, but all eigenstates of p squared are not eigenstates of p. The converse is true, all eigenstates of p are a subset of the eigenstates of p squared. So this is again something you must watch out for. It does not mean that every eigenstate of A is an eigenstate of p. It just means that when you take these operators, as that example shows, you take the one with the smallest subset, and if that forms a complete set, then you are through right there. But if they do not commute, and this happens more often, what can you then say? Then all you can say, they cannot be simultaneously diagonalized, that is for sure, and you cannot find a complete set of eigenstates belonging to both. But you may have some overlap, you may find a few eigenstates which are eigenstates of p of A as well as p. Because in a sense you see diagonalization means finding all the eigenvalues and all the eigenvectors. Well, that cannot be done, cannot be simultaneously. But they may share 2 prime. But they may share one or more common eigenstates. Let me give you an example again from quantum mechanics which you already know. If you look at the angular momentum in the hydrogen atom problem, you know that we will do this, but you know that the states are labeled by a principal quantum number L, by an angular momentum, orbital angular momentum quantum number, principal quantum number n, orbital angular momentum quantum number L, and a magnetic quantum number n. Okay. Now we know that this corresponds to the eigenvalues of the one of the components of the angular momentum, call it Lz. So you know that Lz operator has eigenvalues mh cross. This corresponds to the total angular momentum operator L squared, and this has eigenvalues L times L plus 1 h cross squared. This much you know from the chemistry course, right. Now you know that Lx, Ly do not commute with each other. Lx commutator Ly is actually IH cross times Lz, so they do not commute with each other. Therefore you cannot find a complete set of eigenstates of Lx, Ly and Lz simultaneously, only one of the components. But suppose you look at the ground state in which L is equal to 0. Since L squared has the value 0, it is clear every component must also have the value 0. Therefore the ground state is an eigenstate of Lx, Ly and Lz, all with eigenvalue 0, even though you cannot find a complete set of eigenstates. So they share one eigenstate, but that is a trivial ground state eigenstate. So that you got to be careful about, simply because you should not make the mistake of assuming that if they cannot be diagonalized together, if they do not commute with each other, they cannot have a common eigenstate. That is not true, that statement is not true. What is true is that if they commute, they can be simultaneously diagonalized. If they do not commute, that cannot be done, and that is certainly true. Okay. So we are going to use this statement. Now the fact is, if you go back to our position and momentum example, these two, this statement here, x with p is not 0, it is IH cross times the unit operator. So we have to look to this to see what happens. Then it turns out they cannot be simultaneously diagonalized. A position eigenfunction cannot be a momentum eigenfunction and vice versa. They do not share any eigenstates at all. And then the question is, what about uncertainties? What are these uncertainties and so on? Well, that is not hard to answer, because the uncertainties are just the standard deviations. We will write this down, then we will come back and compute it. Okay. So the uncertainty in an observable in a quantum system is the following. If this variable is A and it is denoted by, it is represented by an operator A, then the expectation value of A, this quantity is equal to, in a state psi is A psi, we know this. I will drop the T for the moment. I am assuming this is a normalized state, so I do not write the denominator down. What is A squared equal to? What is this equal to? Well, that is obviously equal to psi A squared psi on this side. Okay. And what you call the uncertainty, delta A whole squared, this quantity here, is nothing but the expectation value of A minus A whole squared, which is also equal to A squared. Okay. It is just the same as what you would expect it to be, the way you define it in classical probability, the standard deviation, that is all it is, which is the square root of the variance. This is the variance. The only difference is these expectation values, these averages, are taken with respect to a quantum state here, and you need to compute this number. So this is the task, how to find this expectation value, how to compute it. Well, once again the way you do it is to go to a particular basis. In the case of a particle moving in space under a potential, for example, I'd work in the position basis, represent this state psi by the position space wave function and compute these numbers. For instance, suppose I wanted to do this in the position basis for an abstract operator A, what would that be? What would this reduce to? Equal to, what would this reduce to? I'd like to compute this, so I choose a basis, therefore what would this reduce to? What would it look like? At least as a formal expression. Well, simply expand this in the position basis. So write this, write psi in the position basis as integral dx psi of x. I have suppressed the t dependence, it could sit there in psi of t, psi of x times x, of course. So psi equal to, what should I write? What does this become? A bra x psi dagger, that is a complex number, psi star, just psi star, that is just a complex number. Therefore if I plug it in here, what would I get? What should I do? Can I directly plug that in here? You get 2 dx's, what would you do? Well, this is a dummy variable, it is a summation variable, so it is very bad practice to use it twice. What should I do? X prime, call it x prime, x prime. So this would become dx prime, and then I'd have a psi star of x prime, psi of x, that comes from these coefficients. And then now comes the real stuff, the bra vector is x prime, that is on the left, the operator is in the middle, and the ket vector is sitting here, x, that is on the right. So you must be careful with those objects, x prime a x. And what does that reduce to? Integral dx prime. This is just now going to be notation, x prime psi of x, and what does this reduce to? What kind of object is it? Is it an operator, is it a ket vector, bra vector, complex number? It is just a complex number. What does it depend on? What is this object? This is just the matrix element of the abstract operator A in the position basis. It is the x prime xth matrix element, if you like. If this were I and j, you would say this is Aij, but it is the x prime x matrix element, and x prime and x are continuous variables. So I should really write them, put brackets and write them inside rather than write them as subscripts. And I would like to remind myself that this is a function which arises from the operator A, so you will permit me to write this as just A here, as a function of x prime and x. This quantity here by definition is this. So if you tell me how the operator A is represented in the basis, in the position basis, then it is just that integral. Now where is the t dependence coming in? If this depends on t, where would the t dependence come from? It would come from here, this would become x prime t and this would become x comma t out here. Nothing here, this is once and for all the same thing. So our task now is really, we can't escape this anymore, is to find out what the hell is the representation for P. How does P look in the position basis? So let us do that. So our target is the following. We want to compute xp or px if you like, it does not matter. I start by doing the following. I start by saying xp minus px equal to IH cross times the unit operator. That is my input information. And now I am going to find the matrix element of both sides of this operator in the position basis. So let us put an x prime here or an x here, because that is what I would like, and then whatever is inside here and an x prime there on both sides. So xp minus px, and I take a scalar product with x prime on the right and x on the left, these are labels, and that is equal to IH cross the matrix element with x unit operator x prime. But what is that? It is just x prime, because there is a unit operator there, but by orthonormality that guy there is just the Dirac delta function, right. Delta of x minus x prime. I can do a little bit of simplification and then we complete this next time. What does x operator acting on x prime do? It just gives you a number x prime. So that part we can move and say x prime with x p operator x prime. We can't get away from this p, we can't do anything about it, we just leave it, but this x acts on that and produces an x prime which comes out of this matrix element. That is that term. So let us write it to the minus sign, minus x prime x p x prime, that is that term, and that is equal to IH cross delta of x minus x prime. What does this do? What should I do? I do not know what p acting on x prime does, but I do know what x operator acting on this x does. What does it do? It would produce x star, but x is a real number, so it just produces x, x p x prime. So in fact it says xp x prime is a pretty singular object. It is equal to IH cross delta of x minus x prime divided by x minus x prime. It's a pretty horrible object, and of course rigorous mathematicians would shoot me for doing this, but it is actually going to give us the right result. We should be very, very careful working with continuous basis and so on. I have been very casual, but this is a very singular object. What is this equal to? What is this guy equal to, by the way? What is that quantity equal to? Do you know this identity? This is where I am going to do this by slightly non-rigorous argument. What does the delta function look like, by the way? What does the delta function look like? Just a sharp spike, right? You could think of it as some limiting case of a very sharp spike of this kind. This is delta of x. It does not have to be a rectangular window, you just have something with, the width goes to 0, the height goes to infinity in a suitable manner. What does the derivative of this delta function look like? If I have smooth functions like this, then I can define the derivative. What does its derivative look like? Yeah, it actually goes, it goes up. You can see the slope is increasing, then goes to 0, and then the slope is decreasing. So this guy is actually going like this, much worse than this fashion. So you can easily see that delta prime of x can be formally defined as delta of x over x, more singular than the delta function, and in the sense of multiplying by suitable smooth functions and integrating, the derivative of a delta function can be defined, in fact all its derivatives can be defined, and it is just minus delta of x over x. This is an even function, the derivative is an odd function because of this here. It is an antisymmetric function, you can see it goes up and then goes down the other way. So this guy here is in fact equal to minus IH cross delta prime of x minus x prime, okay, d over dx delta over delta x. But that is equal to minus IH cross delta over delta x, x with x prime. So if you now superpose a whole lot of x primes and integrate over x primes with some weight factor, that would be exactly the same as superposing all those guys taking the derivatives with respect to x of this weight factor. So that corresponds to saying that if you give me an arbitrary state psi of x of t and ask what happens to this matrix element, this is the same as minus IH cross delta over delta x, x psi of t, which implies that the momentum operator can be written as minus IH cross delta over delta x in the position basis. If it is true for every ket vector x in this basis, it is true as an identity. Let me stop here. Now we are in shape, because now it's going to be we are going to be able to convert things to differential equations. But I want you to appreciate the fact that x operator in the position basis corresponds to just multiplying by x, but p operator in the position basis corresponds to differentiation. So x operator acting on anything is just multiplying by x, but p does a different thing altogether. Suppose I worked in the momentum basis, what would have happened? P operator corresponds to just multiplying by p, the label, but what would x position operator look like? What does that look like here? Similar argument, but do it with p. After all, the input was just this, so it shouldn't surprise you when I tell you that it is equal to plus IH cross delta over delta p. You differentiate with respect to the label p, but plus because it is x commutator p, that is IH cross, and p commutator x is minus IH cross. So there is an extra minus sign you pick up, and therefore there is this plus sign. This is also a useful thing to know, because we may want to work in the momentum basis, whereas all that p does we will see what the consequences of this are. Yeah.
That relation with xp minus px.
Yeah. Pardon me?
How would we
How did I do this? I did this essentially by waving my hands because this is not a rigorous argument, but it is completely satisfying. I mean, you can make this completely rigorous. Which part of it is missing? This is fine, right? I just, this one, this one, this relation here, that is my fundamental input. It arose because xp was equal to 1 implies in quantum mechanics, when I quantize the theory, xp over IH cross equal to 1. That is the unit operator, yeah, yes, that is input information. That is my definition of a canonically of a conjugate pair of variables in the quantum case.
So in a discrete case that would be a unit matrix.
In the discrete case, yeah, that will be.
In this case, a continuous basis.
What is the unit operator? What is the unit operator? That is really what he is asking. What is the unit operator? What is the element of the unit matrix in the discrete case? Suppose I have an n by n matrix and I ask what is 1 ij equal to, what is this equal to? It is the Kronecker delta for the unit matrix. For the unit operator in the continuous case, these become labels. So what is the corresponding element? The Dirac delta function, absolutely, the Dirac delta function of x minus x prime. That is the xx primed element, if you like. Exactly, because we know this, we know if you took f of x, delta of x minus x prime, f of x prime dx prime, this is equal to f of x. Therefore this is the unit operator, the representation of the unit operator, and that is exactly what I have used there. Alright, so let me stop here.